Welcome back to the module installation and commissioning of industrial robots. So in the first lecture of this module, I showed you a video installing a robot from ground up. Okay, we built a concrete structure, we put the robot on that and finally made it run at the joint level using jogging. In the next lecture, I also showed you how joints are getting calibrated. Okay, so I could calibrate my joints to give the feedback properly to the controller so that you can run the robot well in the Cartesian level. So extending that further, today we'll do end effector calibration. That is the tool which is attached at the end of the robot, end of the serial chain, which actually does the job. Okay, so let me just start with this module. I'll start with a small video recalling what we have done while installing. Okay, so you see, this was the new robot that we received and we could install it. All around it looks like this, and here is it. So you see, this robot came with a bare flange. Okay, so when it comes with this end effector flange. So robot controller knows the center of this flange, that is as an origin of the last frame. That is what it knows. Okay, and it can precisely control that end effector in Cartesian coordinates anywhere in the workspace. Okay, so because it can do forward kinematics using the joint level kinematics that it can do, and it can precisely calculate the end effector position, it can take this end effector to anywhere in the workspace. Okay, so now apart from this, the robot has to do something. So we have to attach, let us say, a gripper. That is what also we did. I'll just show you what we did later on after this. So once it was fully installed, you see, we attached a gripper. It was a two-fingered pneumatic gripper. So now the robot end effector doesn't end up at the flange, which is shown as something like brassy in color. Okay, so that was when it was delivered. Now it also has an attachment, that is this tool, that is the two-fingered gripper. Now it ends up quite further away from the actual position how the robot was delivered to us. Okay, the controller now should know this new position, because now you don't have to control the flange to go to any place. You have to control this new tool which is attached. This will pick up the object. This is which will go on the conveyor and pick up an object. It will place something. If it is a welding tool, that will make contact, or maybe contactless way it does some welding job. Got it? So that is what is the problem, and that is what we want to solve in this particular lecture. So I'll just switch it off. So continuing further, so this is how the robot is delivered. It is with the tool flange included as its last frame in the robot kinematics. So the controller knows till this flange center point, that is the origin. Also the flange orientation is known to the controller where your end effector frame is placed. Okay, the controller can calculate the pose, that is position and orientation of the tool flange during or after completion of any motion. While moving also it knows where it is. Okay, any tool which is attached after this, okay, that shifts the actual position of that flange to the tip of that tool. Okay, so any new tool require the actual position of the working frame of the tool end to be recognized by the controller. Once it recognizes that, now it can be commanded, this new TCP, that is the tool center point, can be commanded to go at any velocity, go to any position, take up any orientation if the flange orientation is also calibrated. So this is our job now. Okay, this point is known as tool center point, and the frame which is attached to this point is known as TCP frame, tool center point frame. Okay, so TCP calibration and identification is required before using any robot, new tool which is attached to the robot. Got it? So before we actually put our robot to use, we should calibrate this step so that the flange doesn't go and reach to the commanded position, and your tool will actually get into the object. Got it? So industrial robots, they allow multiple tools like this. You see, you have multiple tools here. One is here, other one is here, other one is here. So you have 3 tools. Each one of them will have a different tool center point. Okay, and that needs to be taken to the object. So it allows defining several TCPs. However, at any instant of time, only one remains active. You can command, okay, tool number 1, go to this point. Tool number 2, as soon as you say tool number 2, it rotates and makes that as an active. It does all the velocity control, position control, orientation control for that new tool. Okay, so over here it has 3 different tools. Even a single tool can have multiple points which can be calibrated. You can command the center of a 2-fingered gripper to go to certain object, or you can command, let's say, a tip of one of the finger to go to certain object. Got it? So a single tool can have multiple TCP, or multiple tools can have individual TCPs defined for each one of them. Got it? However, only one of them will remain active. So this problem of TCP definitions, that includes 2 particular problem. So it is a TCP origin calibration, that is the tip of this tool, that is this point, that is what I want to know where it is with respect to the flange that I was already knowing. This is the flange with which this robot was delivered. From here to here, what is the transformation which is there? That is an additional transformation. That is what I want to know. Okay, so that is the origin calibration. And also the orientation of this frame, how the new Z axis, new X axis, new Y axis of the new tool is oriented with respect to the flange frame which was there when the robot was delivered. So there are 2 problems. In today's lecture, we will be covering TCP origin calibration. Got it? Okay. So this is one of the very popular method which is there with most of the industrial robots. That through teach pendant, it has a pre-built program which supports calibrating a robot using this technique. How this technique works, basically the TCP, that is the tool center point, the tip of the finger, one of the finger maybe, or center of the finger, the TCP, the point which you want to make a TCP needs to brush against a reference point. Reference point is nothing but a type of reference point which is fixed in the robot workspace, and it has a sharp pointed tip. Okay, so you have to make almost like contact. TCP can make exactly very good, can go very close to that TCP tip, okay, that reference tip, and it can just brush against that from 4 different directions. Okay, so this figure shows exactly that. Let me show you through one of the video once again. So you just notice this. So I am just marking this. Okay, I am placing a mark over here so that I want to calibrate for this point. This will be my TCP. Okay, so now one of the views shows the closer picture of that. So robot is being taken from one of the angle. Actually the process is very slow because you have to take it very gradually to that point. Otherwise you may hit the target and it will move from its location. One of the orientation it has touched, same point TCP. If you can remember, this looks like a dial gauge stand. Yes, it is that. We have made it in our lab, and this is a milled reference point, and it has a switch so that it can be mounted well. It's a heavy tool and it doesn't move if it gets hit, because on a metal table normally we switch it on and it has a magnet and it remains there. Your reference point should be very firm. So now it is approaching from a different angle. So all the 4 angles should be quite distinct. Got it? This is a quick sequence that I have shown to make you understand. Otherwise, it is very slow process because the person has to go at a dead slow velocity when it approaches near to the target. Through jogging, manual jogging, it is done. Now it has approached from all the directions. That's all. So you see it has brushed against the reference point from 4 different directions. Okay, this is what I meant. Okay, the origin of the TCP, that is TCP-X, TCP-Y and TCP-Z with reference to the known tool flange, that is the flange with which the robot was delivered till here, okay, till this one, okay. So that is calculated by the robot controller. So robot controller, once it takes it to any of the location of the TCP, that was the flange, that was the initial TCP, that is the tool flange, is calculated using the robot forward kinematics by the controller, because it knows all the joint angles through the feedback, it knows the robot dimensions, okay, whole of the DS parameter is there inside. It does the forward kinematics and calculates the tool flange location for each of those 4 brushings. Okay. Now, this method is commonly known as XYZ 4-point method. Why, I'll tell you later. Okay. So I have shown you the demonstration video which showed touching that. So the tool flange location can be easily controlled, calculated by the controller. Now the controller also has an inbuilt algorithm with which it can calculate the TCP location with respect to the tool flange. Okay, so how it does it, that is what we are going to do now. Okay, so this is one of the coordinate geometry approach that you can think of, that is a XYZ 4-point method. You can think of a way like, let us say this is your tool, okay, this is your flange, the blue one is your flange on which you have attached a L-shaped tool. Okay, so this is the tip of the tool that you want to make it as a tool center point. Although it is named as a tool center point, it may not be at the center. Got it? It is actually the frame center, that is actually the origin. Okay, so this is what I want to make it. Okay, so now it has approached from 4 different positions. For each of those positions, it has F1, F2, F3 and F4, 4 different sides. So all the flanged locations are shown in this figure. Okay, so use forward kinematics to obtain the tool flange locations F1 to F4. This can easily be calculated using robot forward kinematics. You have already done DS for GP12 robot, you know how to do it. So you can now calculate these locations for all the brushings that it did with this reference point which is there in the robot workspace. Okay, so now you know these points as well. Okay. Secondly, because it is at a constant distance, this F1 to F4, you know it has brushed against the same point that is situated over here, and it should be at a constant distance. This distance is constant for all those brushings, and this becomes the radius. This becomes the radius of a sphere, okay, because it has approached from multiple directions. So this is the reason why 4 brushings are to be done. So you got it, how many variables it has? Because it is a sphere that you want to know. Okay, all the points will lie on a sphere. So minimum number of brushing should be 4. So I is equal to 1 to 4. This is the equation of that sphere which has 4 variables. 3 of them defines the center, that is the ABC location of this reference point tip that is there. That becomes the center of the sphere ABC. Okay, A, B and C goes here, and T is the radius of this sphere. Okay, so this is the minimum set that you need to define this sphere completely. Okay, as the points f1 to f4 will satisfy the equation of sphere, now you substitute all the f1 to f4 locations to this equation and solve this to get the unknowns a, b, c. You can also obtain t, but that may not be useful because it is just the magnitude, it is just the radius of that sphere. So that is not much useful here. So at least getting this point ABC is useful. That gives you the location of your reference point with respect to the robot frame. Okay, that is here somewhere. Okay, so reference point R, that is a vector which can be obtained by R is equal to this. Okay, so you got this R vector. You also had all these locations f1 to f4 vectors, those were known. Okay, so using that you can calculate the vector t, ti, t1, t2, t3, t4 you can calculate. So each one of them will have a different vectors, but the magnitude of that will be the same because that is the radius of the sphere. So ti is equal to r minus fi, simple vector triangle, you can get that. Okay, now use forward kinematic rotation matrix, that is the rotation matrix of this flange with respect to the base frame. So this is it. Okay, so you already have this because you know forward kinematics, you have done forward kinematics now. So this is now much clearer to you. So this is the matrix that is known to you. To find the TCP with respect to the flange, tool flange, so you have a transformation that takes you from here to here. Okay, so now you can do T with respect to the frame F can be obtained using this inverse of rotation transformation matrix into Ti. Ti is this. Okay, that is in this frame. So this one is in which frame? This is with respect to the O frame which is here. Okay, now I want to express this in this frame, that is the flange frame, so that I can get exactly the offset along x, y, z with respect to the existing tool flange. So this is how it is obtained. So yes, this is one of the approach that you can follow, but yes, it is quite difficult to solve this sphere equation and get these variables quickly. So that is the reason there are much elegant way of doing it. So let us start with a new approach. This is what we did. Okay, this is how your TCP is defined with respect to the flange. Okay, you already know this because you know forward kinematics. Wherever the robot goes, you can get this immediately. What you want to know is this with respect to this, that is the offset along x, y, z for this new TCP location. Got it? So these are the symbols that I will be using. I will just go through it. So TF is the homogeneous transformation matrix of the flange with respect to the robot base. N is the number of poses that it is taken while brushing from different directions onto the fixed reference point. TFI, that is the flange homogeneous transformation matrix when it approaches from I is equal to 1 to 4 directions. So TF1, F2, F3 and F4 are there. Okay, TCP X, Y, Z are the offsets. That is what we want to know. We call it TCP origin with respect to the tool flange. Q is the homogeneous transformation matrix of the TCP with respect to the tool flange. Got it? So this is the homogeneous transformation matrix that will include this displacement. There is no orientation calibration as of now. I assume the TCP also has the exactly same frame which is here shifted to this location. Got it? All X, Y and Z will be oriented in the same way as it is there at F. Got it? There is just translation. There is no rotation. That is what is an assumption. That will be done later using TCP orientation calibration. Now we are just interested in this. Okay. So let us begin. The homogeneous transformation matrix from flange to the TCP location is given by this, that is Q. I call it from now on, instead of calling it this way, I simply will call it as Q. So it is nothing but translation along X, along Y, along Z. This is your homogeneous transformation matrix. Quite easy. Okay. That this TCP has burst to the same reference point from 4 different directions, 4 attempts. So Q remains the same, both the sides Q remains the same. What changes it? From the first direction, from the second direction, from the third direction, this frame location F1, F2, F3 and F4, okay, so that changes. Okay, so that actually changes this first matrix, that is the transformation matrix of frame I with respect to the robot base. So this is what changes. So your robot now is at a new location. This is what is known, that is the transformation of frame location with respect to the base for ith contact that it established. Okay, so this is what you know for every instance. From here to this point is your Q. Okay, so in order to reach till here, because this is your reference frame, this is same for every directional approach. Okay, wherever you are approaching, you are reaching to the same point, that is this reference point R. Got it? So this is your forward kinematic transformation from the robot base to the flange location for ith contact, and Q is the matrix which is here. Got it? That will finally take you to R. R is same, so that makes the last column of these two directions exactly the same. Assuming this and this both like this, so I have just assumed once you take the product, you get to a matrix that looks like this. It's a 4 cross 4 homogeneous matrix. Normally these terms will be 0, this will be 1. This will tell you the translation, this is the orientation matrix. That's a standard structure of any homogeneous transformation matrix. So let us say from A direction, orientation matrix was like this, this was your translation. And similarly from the B direction, you have a matrix that has a structure something like this. Okay, so these two are rotation matrix of the tool flange from I and J directions. I and J are the two different attempts. FA and FB are position vector of the tool flange for I and J direction. That is the position vector, FA and FB. Got it? So that is basically connecting the base to the tool flange. Got it? So this will give you the orientation of that, this will give you the displacement of that. Okay, so if you expand this, taking product with the Q contains TCPX, all the direction. Let me just show you once again. This, it looks like this. Got it? So this is your Q, this is your Fi that goes before to this. So once you take the product, it looks like this. These are 3 scalar equations. Top 3 rows is just written like this, expanded like this, and you get to this. Because both are same, A and the B part, so it is written over here like this. These are the 3 scalar equations. Rearranging, you can quickly get to this. I have just rearranged, took some common, that is TCPX here and here, TCPY here and here, TCPZ here and here, and same for all the equations. That can be in a compact way. It can be written like this. So that is nothing but RA and RB. Those are the rotation matrices. This is the column containing TCP location. These are the flange location. FA and FB are the position vector of the tool flange for I and J directions. So these are there. Okay. And if you take inverse of this, bring it here, it becomes like this. Got it? So this is your inverse. It is something like inverse. I'll tell you what it is. It may be a square matrix, then it can be quickly calculated taking inverse. Otherwise, there are other approaches to do it. I'll tell you how. So yes, this is your equation. This needs to be solved in order to get TCP location. That is what we are interested in. So the matrix RA minus RB as given in this equation is normally a singular matrix. If it is just two directions, you are establishing a contact, and this will result in no solution at all. This is the reason why it is brushed from 4 different directions, and all the directions should be quite distinct, okay, to create 6 linear equations. So I have taken first and second contacts over here, third and fourth contacts over here, and TCP location is like this, and this is here. So it effectively creates 6 linear equation. So now the term in this equation is obtained by QR decomposition, or it can be LU decomposition method, or pseudo inverse technique if it is not a square matrix. Otherwise we can simply take inverse. Okay, but over here it is not a square matrix. You have to go for one of these techniques to find out the inverse. Okay, and finally we get to this. Got it? The accuracy of XYZ 4-point technique is, you see, it is operator dependent, because you manually jog. Using your eye estimation, you can just see whether it is making almost like contact from 4 different directions. Okay, so that is what is the problem. So human precision does matter over here. Okay, that is what is making it too much operator dependent, and it is not very accurate, but quite good for quite number of applications like pick and place and those kind of application. Okay, so what additionally manufacturers have provided are TCP calibration toolkits, like ABB has provided Bullseye. I'll show you a picture of that. How does it look like? So it looks like something like this, you see. So it is you see, it is a frame which is in both the direction. There are sensors which can precisely check the location of the TCP with respect to the base frame. This calibration tool itself is already calibrated with respect to the base frame. So yes, this is the way. You just need to take your robot in between that frame, and it can detect the tool TCP. Okay, so this is ABB Bullseye. Similar is KUKA TRACC, KUKA track it is known as. So it has okay, 2 different stands which are there, which looks like a frame. You have to take the robot tip in between, and using sensors it can detect the TCP location very precisely, and it automatically updates the location in your robot controller. Okay, so using this you can save a lot of time and make the things very precise, and this is very good for calibrating any welding tool. Got it? So there is another technique which is known as XYZ reference method. In this method, a new tool is calibrated using an existing precisely calibrated tool. Okay, so let us say you already have a tool which is precisely calibrated against the flange. Okay, once you have fitted it, it is calibrated. You want to change this with a new one. This eliminates brushing the reference point from different directions to just one direction. You now don't need to brush it from 4 different directions. So the probability of error getting carried over to the robot TCP calibration due to the manual error is less in this case. It is very less time consuming because you are just brushing it from one direction. So it also reduces the downtime when you exchange a tool to the other tool. So less chances of error while replacing the tool with the new one, and it is just a 2-step process. So brushing the existing tool, which is a calibrated tool, before unmounting to the reference point. Before unmounting, I'll take it to a reference point. Okay, and then I'll brush the newly mounted tool to the same point. Okay, So this is the brushing of existing calibrated tool to the reference point which is there in the workspace, and the new tool. Okay, now you unmount this and put the new tool and again take it to the same location. So hope you got the idea what it must be doing. Actually it is calculating the location of this reference frame. Okay, so once you put the new tool, so you are taking it to the same location. That means you are taking to a new vector. So we'll do good analysis of this now. So how it works is very simple. The TCP of the existing tool before unmounting from the robot flange is made to brush to the tip of the fixed reference point. So this is the reference post, this is the point which is here. Got it? So yes, so what it actually had done when you did that job, it found the location of the reference point. So it found the location of this point. R is calculated using this. So what is this? This can be obtained using, this is what? This is the position vector of the tool flange with respect to the robot base, obtained using forward kinematics. So you have obtained this, quite easy. Because it is a calibrated tool, so you already know what is T1. So T1 is for the known tool, it is already known. So you already know T1. Okay. So you just take vector sum and you can reach till this point. So you calculate R very easily. Got it? So you got till R. Now that you know R, now you are ready to take it out from the flange and put your new tool. Okay, so that is what is the second step. So new uncalibrated tool is now mounted to the robot flange and it is made to brush to the same reference point at R as we have obtained in the step 1. Okay, so we can identify the new TCP location T2. So this is your identified T2. How it is identified, you just see. Now again F2 is the position vector of the current tool flange with respect to the robot base. This again can be calculated. Even with the new tool, flange location you know can be calculated using forward kinematics. So we did this, we found out this. Got it? The reference point R was obtained in the first step. So now you know R, you also know F2. Now you can calculate this T2. So this T2 is now identified. But now this T2 is in this frame. This is the vector which is expressed in robot's base frame. But I want to achieve what? I want to find it out in robot's flange frame, this frame. So how to obtain that? From here to here, this vector I want to know. So how to obtain that? So that is what can be obtained using forward kinematics, rotation matrix again, 0 to Q2. So this is known using forward kinematics. Okay, with respect to the frame F2, TCP with respect to frame F2 can be obtained like this. So F to T2, this transformation can now be obtained using this. You just take inverse of this. This can be expressed in the flange frame like this. So this is how you can quickly obtain the TCPX. So what is this? This is nothing but a vector of TCPX, TCPY and TCPZ. Got it? So this is what is obtained here. That's all. So you see, it is quite easy to do using multiple techniques. Few of them are supported by some robots and some other robots may have some different way, but idea remains the same. You have to get to this point, that is the TCP point with respect to the flange. Got it? So that's all for today. We have already calibrated our TCP origin. In the next class, I'll tell you how to get the frame orientation, that is the TCP orientation with respect to the robot end effector flange. Okay, so that is what we'll be doing in the next class. That's all. Thanks a lot.